Okay, what was the other one you were interested in?
Sine t over t squared.
No. Sine t squared over t.
Is that a different one they had on one of the other ones? Okay, so we'll go back. Okay, so you've got the, I think everybody's got the tools to go with this one, right?
No.
You do. When we're in the lab, I can give some individual hints.
Sine 2 over t, and they put in the 0 which equals 1, and then 1 squared is 1. Is that what it is?
Let's just maybe go. Excuse me. So you
I don't know how you
I'm not even. He's just like, you know what? It's like, sure. I don't know.
Okay. Yeah, this is, okay. Right, so this looks really similar, doesn't it?
Yeah, but wait,
Okay, what about this one?
Isn't that the problem?
No, different. Different. Okay, it is. The answer is 0. I'll tell you that, but I don't care what the answer is. I want to know how you're going to get the answer. Well, I'm not going to do the whole problem, but I want you to do the problem, but I'll help you get this set up a little bit. Okay, I would rewrite this one with parentheses. I think that's helpful. Okay, so here's kind of my hint on this one now. We've got to get this to look, we have to get to the form limit of sine theta over theta as theta approaches 0 equals 1, right?
Yeah.
Okay, so let me ask you this. What is theta going to be in this case?
T.
Okay, is it going to be t? Now this maybe, but what are the two options for theta?
T or 0.
T or t squared, right?
Okay.
Okay, agreed, because we've got to get this thing, we've got to get the sign of, the argument of the sign to match what's on the bottom, right? So we have to choose what our theta is going to be, and we have to somehow get this to look like that. We've got to make a choice though then. Are we going to let theta equal t and try to make a change up here, or are we going to let theta equal t squared and somehow try to get that to be t squared? Now, what do you think is harder to do? Let's think about this logically. Knowing what you know about trig, is it more difficult to change something inside of a trig function or outside of a trig function? Outside, for sure, right? So we want to let, this is going to be our theta right here.
Yeah.
It's going to be a t squared, okay? So in order to get it to this form where we can reduce the indeterminate, eliminate the indeterminacy, we get the bottom to be, what are we probably going to have to do on the bottom? We're going to have to get a t squared on the bottom. But we can't just multiply the bottom. We got to multiply by 1, which means top and bottom, right? Okay.
So it would be like t sine.
Right. Okay, I'll let you take it from there. And then the other thing is, when we somehow eventually get a t squared on the bottom, and that we're going to have to do some stuff to do that, then what about this? That doesn't look quite right. It doesn't, but go ahead. Alexa, do you have an idea? And that's okay to do, isn't it? Because wouldn't you agree that as t goes to 0, so must t squared go to 0?
Yeah.
Okay, good. All right. So you're set up for that one. Okay. What about this one? Take a quick look at this. Okay.
And also the one that is like
Okay? This is, once again, what form is this probably, do we have to make this look like?
A little fraction thing.
Same thing, right? We've got to make this look like a limit of sine theta over theta as theta approaches 0. Same issue as before. Is our theta going to be an x, or is it going to be a cube root of x? It's going to be x, isn't it?
Yeah.
Right? Because that's what's stuck inside the sine function. So we've got to do something, we've got to multiply this fraction by something that's going to make the bottom look like what?
X.
X. Yeah, right now it's x to what power?
The third.
The 1/3. You got it. Okay, that's enough information to go on, I think. Okay, there's one other one.
Yeah, the one where it's like sine of like 13 or sine of 14. And the
Oh, yeah,
answer is
yeah,
13
okay.
over 14.
Okay, yeah, we'll just make one of those up. So what if we've got something like this? What if we've got the limit of, let's just say we got the limit of sine of 5x over sine of 2x. Okay, what are you going to do?
5 over 2.
As x approaches 0? Okay, so yeah, what are we going to do there? Now this one, somehow we've got to make this, well, are we going to be able to do this in a single limit? Probably not, right? Probably not. We're probably going to have to break this into multiple limits. Okay, so this is probably a good one for us to go through as a group. It's after we're done, you're going to think, okay, it's not so bad, but I think there's some stuff here that maybe we should see together. So if we break this apart into two separate limits, the limit of sine 5x as x approaches 0 times the limit of 1 over sine 2x as x approaches 0. Make sense? So let's deal with those one at a time. What about the first one? What's my theta going to be in the first one? 5x, right? So how am I going to get a 5x on the bottom? Say it again, kid.
5x.
Okay, but I can't just multiply the bottom because that's changing the fraction.
1 over 5x.
Top and bottom by 5x, right? What if I multiply top and bottom by 5x? I've just multiplied sine 5x by 1, so I haven't changed it, right? I haven't changed the value, let's say. So then this becomes limit of 5x times
Sine of 5x, right? Yeah. Over 5x?
as x approaches 0,
No.
5x, because as x approaches 0, so does 5x, so that's a freebie, right? We can make that transition.
Wait, why do you have a 5x on the outfit and 5x
Because
on
that's
the
a
bottom?
theta.
Well, because I've got a 5x, I have to multiply top and bottom.
But it's just at the top.
Right, the bottom one I want to kind of include with that sine 5x because that's our standard form, right? That's our known limit.
Okay.
Now does that make sense? That's our sine theta over theta,
Oh, okay.
right? Times. Now what about this guy over here?
Multiply by 2x.
2x over 2x, how about? Okay, so we're going to multiply top and bottom by 2x, and that's going to give me limit of 2x over sine 2x. And then I've got a 2x on the bottom also, as what goes to 0? 2x. Okay, so let's see if we can resolve this then. What's going to be the value of this limit as x approaches 0? 0. Okay, this one's a little bit weird though. It's upside down.
Wait. What?
Okay, right. There's two ways you can think about this. First of all, I'm going to do this strictly, from fundamental principles. We're going to do this just in terms of the known limit, the one known limit that we have. And based on this answer, we're going to maybe expand the possibilities for what we can do with our sine theta over theta limit. Couldn't I rewrite this if I divide top and bottom by 2x? I could rewrite this limit right here as one over sine 2x over 2x. If I divide top and bottom each by 2x, 2x over 2x is 1.
Okay.
Sine 2x over 2x is sine 2x over 2x, right?
So we just broke it up some more.
Right. What I did is, but now this is a known, this limit is known, isn't it? This is just 1, right? Okay, so now when I take my limit, this one goes to 1, but Zoe made a good point. I mean, do we really have to do that?
Yeah.
I mean, because 1 over the reciprocal of 1 is 1, right?
Oh, and that's the reason for that.
Exactly. And so really what we can do, and I think this is perfectly fine to do, I really do. I don't think there's a problem with this. I think we can make this statement. We know that's true, right? So if we ever see something like this, the limit of theta over sine theta as theta approaches 0, what's it equal to? 1. I think we can write that without having to show anything. I think that's fair game. Okay, because reciprocal of 1 is 1. Make sense? Question?
So, scroll up.
Yeah, scroll up.
So, shouldn't sine 5x over 5x equal 1?
Oh, I'm sorry, it is 1. Sorry, I don't know why I wrote it. You're right.
Because the whole answer is 0.
Okay, you're right. So, okay, hang on. We're not done. We haven't really resolved the whole issue yet, though. We've eliminated the indeterminacy, right? But now we've got some other problems. So we got some other things to worry about. So now we've got
Well, the answer is
1. Is it 0? Hang on. Is it 0?
Yeah, because 5x is 0. When you put the 0 in the 5x.
Okay, but hold that thought for a second. So now we end up with
Okay, 5x over 2
the limit of 5x as 5x goes to 0
is 0.
times the limit of 1 over 2x as 2x goes to 0, which couldn't we just rewrite that as this? We could rewrite that as, these parts are gone, they're just 1s. We could rewrite that as the limit of 5x over 2x as x goes to 0, right? Right, now,
Yeah.
what's wrong with that?
Nothing.
It's 0 over 0, but it's an easy one because look, there's our factors. So what's our answer? 5 over 2. Yeah.
Wait, but if you put the 0 in.
Yeah, okay, right, okay, but if you put the 0 in, okay, but let's look at this, let's focus just on this limit for a second. Okay, so agreed. Now listen, please. I know there's lots of good discussion going on, but just hold on. Hold your discussion for the group. If I try to take this limit directly, I get 0 over 0, which means more work. I've got to cancel something, right? Well, there's my cancellation. I can cancel the x's top and bottom. So they're gone. Now, what's the limit of 5/2 as x approaches 0? Good. What's the limit of 5/2 as x approaches 17/2? 5/2. What's the limit of 5/2 as x approaches -5? Doesn't matter what x approaches, does it? Because the value of the function is just 5/2, right? Okay. Make sense?
So it does need more work, but it's easy work.
Exactly, but it's easy more work. Exactly. Okay. Make sense? Sort of, kind of, maybe?
If the x's were like real numbers, you could just cancel them and use the x's.
Say it again.
How the x's instead of like we do like 17/2.
Oh, well, it doesn't, my point was just that it doesn't matter what x approaches if there's no x's in the limit. Okay, yeah. We good?
No.
Oh, question.
Can you, I know that's kind of similar to the question that we were like, when we used the cube root of x.
The cube root of x. Oh, yeah, the cube root of x one. Okay, so here's the question. Okay, so I'll go back a little bit. So we were looking at this one, right? What if we rewrote this as the limit of sine x over x to the 1/3, right? As x approaches 0. What do I have to multiply top and bottom by here to get x on the bottom? That's my theta, right?
3.
Say it again.
X.
X to the 2/3.
What the?
Yeah, because you add that when you multiply.
Right? Because, yeah, when you multiply like bases, you add the exponents, right? Okay, so
Well, where do you get the 2? 2 over 3.
Because you want to fill it.
Wait, what? I've already solved.
that's just x, right?
Yeah.
Okay, you take it from there.
Oh, and then it's
Wait,
just,
one second, I gotta write this.
Times.
oh.
Okay.
Oh, okay, so it's
All right, here we go. New stuff.
Oh, no.
New stuff.
Oh, already?
Already. Okay, so put on your thinking caps. Let's look at this. Okay. Okay, hold off on the other stuff for now. You can work on that later. We'll be in the lab tomorrow. You can work on, you can have some specific questions, answer in the lab if you need to. I want to look at the next stuff though. We're going to move into, this is in the book, I think it's section 1.4. Has to do with continuity. Really, really important concept in math, continuity. Before we jump into anything really highly mathematical and abstract, let's just think of what a continuous function means at a really simple graphical level. Who can sketch a continuous function for me? Okay, there, I'll just do that. That's one of them, isn't it? If I take, say this is the xy plane, if I want to sketch a continuous function, let's say I know that the function passes through that point and through that point. What has to be true if I'm going to sketch a continuous function that goes from there to there?
Can you put just arrows on your answer?
Well, I could.
It goes beyond just.
Well, it might, but maybe the function's only defined from this x value to this x value. We don't really care what happens to the left or the right of it for now. What I want to focus on is what's happening in here. First of all, if it's a function, if we are going to restrict ourselves to this being a function, what do I have to be careful of?
X values for
Okay, so I have to pass the vertical line test everywhere, right? Okay, the vertical line can only intersect the function in one place everywhere. But what else has to be true if this is going to be a continuous function? What about the pen is important?
Oh, it never leaves.
Yeah, it never leaves the board, right? That's really, in my mind, a great definition of a continuous function. A continuous function on an interval from A to B just means that I can draw the function from A to B and my pen never leaves the board. Okay? Makes sense, right?
Yeah.
For it to be discontinuous, I would have had to have picked my pen up, and so if I don't do that, it must be continuous, right? That's it, okay? So what we want to do though is now we want to take that simple graphical concept and we want to put this into an algebraic definition that's going to allow us to use it rigorously, right? That's probably not good enough for us just to say a continuous function is one where we don't pick our pen off the board, because how are we going to apply that to some specific problems where we're given functions in terms of x's? I mean, that doesn't make sense, right? We got to be able to do more than that. So we're going to take this idea, we're going to make it more abstract. Let's first of all start off with a little conversation here. How could a graph be discontinuous? What are some ideas?
Oh, like.
Raise your hands. Let's get some ideas. Throw some ideas out. Yes, ma'am.
A break in the function.
Could have a break in the function. Sure, that would work, wouldn't it? What else? Say it again. Could be a piecewise function, which would be let's call that a big break in the function. There's going to be a major rift in the function. What else could happen?
Like an exponential.
Okay, I could have an exponential function where it's undefined. Let's say we've got like an asymptote, you mean? So we could have an asymptote where the function is undefined at a certain value. right? Can we think of an easier way that a function might be undefined at a certain value?
Dividing by x when the function is going over the y-axis.
When it's, so,
When it crosses the y-axis.
so in other words, it's gonna be an inverse function, which would cause that.
When you have like 5x divided by x.
Oh, I see what you're saying, okay.
When like when you need like off.
Okay, so I'm gonna translate that into what it might look like, that's exactly right. But what about just a hole in the function? That would work too, wouldn't it? Right, if we have just a single hole in the function, that makes it discontinuous. We could have it be much more discontinuous if it's a piecewise function where it's got a big break in it, right? So let's see if we can draw some of these graphs, what these are gonna look like. Examples of discontinuous graphs. Let's start with that easy one, right? I mean, if I've got a hole in the function that makes it discontinuous, let's go ahead and just, let's say we're starting at A, and we're going to travel along, and there's a hole in the function, and then continue on to B. That's discontinuous. It's a really small discontinuity, but it's discontinuous, right? I still have to pick my pen up for that one point and skip over it, okay? We had the idea of a big break, a big discontinuity, a break in the function. So we could do something like this, where we go, say we're going to be there and there, right?
Yeah.
Okay, agreed? All right, let's just pause there for a second. So how would we describe this? What's our condition then for this kind of a discontinuity? What happened there? The function was undefined, wasn't it? The function doesn't exist for whatever value this is. Let's call it C. Function is not defined there, doesn't exist, right? So the function is not defined at C. F of C doesn't exist. What about here? How do I describe what's going on there? Sure, it's a break in the function, but how could I write that in a way that's how are we going to flag that in a way other than just by looking at a graph? What do you think?
just go.
Sure. So what do you think? How is this one?
There is only one solution at C.
Well, okay. Would you agree that this function is defined at C, right?
Yes,
Okay.
only one. There's like both sides aren't approaching C.
Okay, yeah. Now, what kind of an animal do we use to describe approaching from both sides? What is that? Limit. Yeah. I heard it. I heard it. Who said limit? Somebody said limit.
I
said ant, yeah, let me.
Okay, there. So I'm thinking ant limit. There we go. Okay, so. Okay, so would you agree then? Does a limit exist at C there?
Yeah.
Well, hold on now. Nope.
Somehow.
Okay, because let's review for a second. Remember, our definition of a limit implies that the ant is going to. Say it again.
It goes to knows where it's gonna, like.
It knows what it anticipates stepping on the same place from both directions, right? So the ant walking from the left thinks he's going to end up there. The ant walking from the right thinks he's going to end up there. It's irrelevant where he ends up, but they anticipate stepping in different places, and so maybe a good way to flag a situation like this, if we want to catch all of those, the condition that we could say that's not being met there, that's causing this to not be continuous, is that the limit doesn't exist at C, right? If a limit doesn't exist there, that must mean that the ants are thinking that they're approaching different values from either side, right? So, right?
Right.
Okay. So the limit of f of x as x approaches C doesn't exist. Okay. Because they each think they're going to end up at different places.
Okay, yeah.
Agreed? Think we got them all then?
No, I think there's one more.
Think there's one more? Because there's another, looks like there's another spot down here. Okay. Okay, we think we got them all, but I'm gonna throw one more at you. I want you to categorize this one. And that's supposed to be right in the middle. Let me fix that.
Isn't that the same one?
No, almost. Not quite done.
Yes, that one is good.
Okay, it's still discontinuous, isn't it? I have to pick my pen off the board. Why? Which of those conditions does it fit one of those conditions? Let's see. Does it fail that one? No, the function exists at C, doesn't it?
Yeah, but there's, it doesn't.
What about that one?
What's that?
Does the limit exist?
Yeah.
Ah, okay. But then what's the problem? There's still a break.
Yeah.
There's still something's wrong.
Could it be like the function doesn't agree with the limit?
Yeah,
Is
That's
that
it.
honestly the answer?
that's it.
Why did you know? Wait, say that again?
Okay. Let's say it again. It's not enough for us just to say if we only had these two criteria, this guy still slipped through the cracks, right?
Yeah.
Just saying that, well, kind of literally. Just saying that the function has to exist and the limit has to exist wasn't enough because both the limit and the function exist here. But the problem is, in this case, the limit of f of x as x approaches c doesn't equal f of c. The value of the function and the value of the limit do not agree. Okay? To me, calculus books always list all three of these criteria, but to me, the last one is sufficient. Because doesn't the last one imply that if this is the only rule that we have, doesn't that imply that both the limit and the function both exist there?
Yeah.
Right? Does that make sense? So I really think that's the only one you've got to remember. This one obviously breaks down if there's no limit, then you can't even, right, then you're done. You can't have this relationship. If the function doesn't exist there, well then you still can't have this, right? But even if both of them do exist, they have to agree. Yeah.
So when you're saying like it doesn't agree, when it falls through the cracks and the limits like not, is it just like?
Okay, when I said fall through the cracks, I didn't mean anything specific about this problem. I just meant that we didn't define our rules carefully enough. They found a loophole. The math gods found a loophole there. And they said, oh, okay, you think you're pretty smart. You got these two criteria. Well, what about this guy, right? This third example passes both of the first two criteria, but clearly it still had a discontinuous spot, right? It was discontinuous. So we have to add the third condition, which is that both the limit exists, the function exists, but they have to agree, okay?
But they don't agree.
And they didn't in that case, right?
And then that's an exception.
Say it again.
Is that a rule then?
Well, this is what we would say. These are the three criteria for continuity at a point. So let's summarize these. So on the next page then, this is kind of what your book says. So why is that not showing up? Definition of continuity at a point. Let's go through this. A function, well, that looks terrible. That's supposed to be an f. Wow. A function f is continuous at c. So at the value x equals c, if the following conditions are met. If f of c is defined, check. If the limit of f of x as x approaches c exists, and if the limit of f of x as x approaches c is equal to the value of the function at c. If those three criteria are met, guaranteed, the function is continuous at x equals c. Okay?
So the things we just learned are things that cannot happen.
Right. What we just looked at were the graphical examples of what happens if each of these three criteria are not met. This was, we had a hole in the function. Or it could be an asymptote too. This one was, we had a break in the function. This one was, we had a hole in the function, and then the point was defined as something else, right? That x value. Those are the only three ways that we can be discontinuous, though. If we can meet all three of these criteria, we're good. The function has to be continuous at that point. Okay?
And then if they don't, then it's not.
Then it's not continuous, right? So let's go back this a different way. You tell me. Let's try a couple of these.
Wait, should we write this down?
Oh, you don't. I mean, this is all going to be. It's all in your book, and it's all going to be on the video. And I've saved these. I haven't made PDFs yet, but I've saved these, so I can make PDFs out of these too. I will. I promise I will. Right away. Okay. So what about this one? You tell me, why is this function? Is it continuous? If not, why is it not? Don't say anything out loud. Don't say anything. Hunter, you were shaking your head. No, why not? Okay. Right, okay, so which of those three criteria, I slipped you kind of a tricky one here. Which of those three criteria is the one that this fails? True. I guess you could say that too. The limit doesn't exist. Does the function, I mean, it fails all of them. Does the function exist? No. It doesn't exist at C, does it? It's undefined there, right? Because it's an asymptote. Make sense? So that one fails for every conceivable reason.
Sweet.
Okay. What about this guy? What's going on there?
So,
What's it going to be?
number
Number one, which was what?
X is defined.
Okay, function's undefined at C.
Yeah.
F of C doesn't exist. Okay. How about the pink one now?
Okay, so
F3.
number two.
Okay, number two. Okay, so raise your hand. Somebody give me be brave. Someone's going to say, yeah, you're right. What's number two? Right here. Number two.
Number two, what is it? It doesn't exist.
The limit of the function doesn't exist at C. That's true. Is there another reason? What is it? Right. Right. It fails 1 and 2, doesn't it? Because I've got a hole here and here.
So these are all.
Hey, too much talking. My goodness. Right, so this one fails both. Either one's a good answer. All you have to do is fail one of them, and it deals off, right? Okay, so now what if I do this?
Deals off.
Just two.
Fails 2. The limit doesn't exist because even though the function is defined there, the limits from the left and the right don't agree, right? Okay, so let's go back to the blue one. And what about now?
This was the
So
third
that's
one.
number
Third
three.
one. Okay, so what is the third one?
It's
The function is greater than
Good.
Doesn't equal the function.
Janelle, you say it for all of us. What's it going to be?
Oh,
Without looking, just don't look up.
The limit of f of x doesn't equal f of c.
Good. The limit of f of x as x approaches c
Yes.
doesn't equal f of c. Perfect.
Yeah.
Okay? So the limit and the function don't agree at c. Okay. All right, so next issue. Next issue. So that's useful, right? But all we've really done there is we've defined continuity at a single point. I mean, that's really not an ambitious enough goal for us based on what we talked about at the beginning, though, is it? We wanted to talk about how we can replace this notion of being able to start at one point and never pick my pen off the board and end up at another point and have, that implies a continuous function. But all we've done is just said, okay, well, at one of these points on here, call this C. Okay, so that point, the function is continuous there. That's not there yet, right? I mean, we want to deal with the whole thing, the whole interval, right? So how are we going to do that? What about continuity on an interval? So now, could we say that a function is continuous on an interval somehow?
Yeah.
What has to be true for the function to be continuous on the entire interval?
All points need to be defined.
Okay, true.
Never, they meet all three, they pass all three tests.
Okay, now when you say, everybody listen, when you say they pass all three tests, who's the they?
The function.
Okay, the points on the interval. Would you agree that if every point on this interval passed all three of those tests, then there's no way that this function could be discontinuous on that interval?
Yes.
Agreed?
True.
So that's our definition then, right? We can say that if it's continuous at each point on the interval, then it's continuous on the whole interval. Okay, but do you see a problem with that?
What about endpoints?
What about the endpoints, right? We have a problem with the endpoints, don't we? Where's our problem? Now, raise your hand. Don't say this out loud. I want to make sure everybody. So, what's wrong with the endpoint? With the endpoints here? What part of our definition works every place great except at the endpoints? Right.
Limits don't define.
Yeah, the limits don't exist at the endpoints, right? How come they don't exist there? Okay, because the ant can't approach from both directions because he's got no place to stand left of the left endpoint. Agreed?
Yeah.
Okay, so go ahead. Question?
If we had an arrow on the end, then it would be okay?
Okay.
Or does it have to be an open circle?
Well, okay, both excellent questions. I'm gonna take the first one. Just everybody think about this for a second. What if the function goes forever, right?
That it's continuous.
Then it would be. But what if the function is only, for whatever reason, we have only defined that function on this interval? Now that's possible, right? That's possible because what if, for example, if we were going to look at the strength of a gravitational field acting between two particles as a function of their distance apart. Okay, it would look, if we did that, it's going to look something like this. It's going to look something like that. Okay, actually that's probably a bad one to pick. Bad one to pick, hang on. I don't know what I was thinking there. Gonna do a better one. Let's do, okay. Let's do the area of a circle as a function of r, or a function of x. There it is. Okay. What's the function that describes that? Okay. The area of a circle is, or let's make it a square. How about? Let's make it the area of a square of side length x.
S.
It's just x squared, isn't it? Right. So if that's x, this function f of x equals x squared. Well, does x squared exist over here?
No.
Well, x squared does. The function does, right?
Oh, yeah.
But in our particular case here, this is a geometric issue. In the case of this geometric issue, you can't have a negative radius, right? Or a negative side length.
Yeah.
And so I'm going to say that's similar to what Cheyenne's proposing here.
Yeah.
What if the function continues, if it really does continue off to the left, then it is continuous at the endpoint. But say we do have an endpoint there. Our interval, for whatever reason, we stopped it there. We have a problem because the limit doesn't exist, right?
Right.
So, are we almost done?
Yeah.
Okay. So that's the last issue we got to deal with. What we can do at this point, though, would you agree? What we can do at this point is we can stop here comfortably. We could define continuity on an open interval as long as we don't include the endpoints, right? So we could say this for today. A function is continuous on an open interval when x is greater than a and less than b, if it's continuous at each point inside the interval, in the interior of the interval, right? Okay, next time we deal with endpoints.